On our worksheet, where we left off yesterday, we were grinding out the specifics about item 3. We started with a decimal value of 255, which required a 64-fold increase. If we're increasing, that means we bit shift to the left. If we're doing 64 times the original value, the exponent of 2 that equals 64 is 2 to the 6th, so it's 6 shifts to the left. The binary value of 255 is 1111, 1111. Or the hexadecimal value for all ones in each nibble is FF, foxtrot, foxtrot. If we slide this value 6 to the left this way, I'm going to have to create 6 zeros here, 6 trailing zeros, and that's what you see down here. 1, 2, 3, 4, 5, 6. That bumps 8 of these ones to the left, and on the last leftmost nibble, you just see a 1, 1. We add 2 zeros as leading zeros just to preserve the good practice of leading and trailing zeros. And that gives us a binary value of 0011. We know for a fact that this is hexadecimal value 3. We already know from our table that 1111 is F, and then 1100 is C, and all zeros is 0. So our new hexadecimal value is 3 foxtrot Charlie 0 for that 6 place left bit shift. And if you say that 5 times real fast, you probably say something naughty and you don't mean to, but hey, just saying. Okay, keep things lively. All right, how do we convert this to decimal? Well, if we take each place of the hexadecimal columns, this first column is 16 to the 0 power, or 1. 1 times 0 is 0. Well, that's easy. Charlie in hex value is equal to 12, but it's in the 16 to the first power column, which is equal to 16 times 12. So if I take my calculator and I put 16 times 12 and then store it in the memory, because this time the memory is empty. Going to minimize that for a second. I'll go ahead and take the next value. The next value is the third column of the hexadecimal value expressed, 16 squared. 16 squared is equal to 256, but foxtrot is equal to 15. So 15 times 256 is what I'm going to calculate next. 15 times 256 equals 3,840. I'm going to add this to my second column value by clicking memory add. So now if I reclaim the memory, I'm going to have something that's bigger than 3840. So far my subtotal is 4,032. If I take the last column, 3, the hex value 3 is in the fourth column. That's the 16 cubed column, 16 to the third power. 16 to the third power is 4,096. So if I take 4,096 and multiply it by 3 and add that to my subtotal, I should get this. So I'm going to go ahead and clear this. I'm going to take 4,096 times 3 is equal to 12,288. I'm going to add that to my previous subtotal. Click it once. Memory recall, 16,320. And voila. How can I be absolutely sure, or if I want to cheat on the upcoming assessment, and no, please do not repeat to my chair in the department, or the dean of College of Science and Math, or the provost of the University of the Virgin Islands, or the president, or the board of trustees, any of those. Please don't say Professor Kentop told me to cheat. But I do want to give you an easy button. You can use the scientific calculator, and no, not the scientific, the programming calculator, and you can click on decimal and then put in the original 255. That gives you the hex and the binary values, and then you multiply it by 64. And you get your ultimate check to see that what you did manually is correct. You have a hex value of 3 Foxtrot Charlie 0. You have a decimal value of 16,320, and your binary value is 0, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0. And yes, you got to keep the places trailing zeros intact, because if you didn't, then it would be a much smaller binary value and you wouldn't get the same thing. Are there any questions about item number 3 on the worksheet before we continue?
None from me.
No.
I just had a quick question,
Yes.
Professor Kantop.
Yes.
So I realized for like the answers that you have, every four digits you have a space. Is that what expected of us to do when we're giving the answer?
You know, that's a wonderful question. See how in the calculator it's got an extra space in between?
Yeah.
That just helps you visually parse out the nibbles, the half of a byte, right? A little more efficiently. So I always include an extra space just because it makes my answer cleaner and more discernible. But you don't have to. So the short answer is no, you don't have to, but it's just easier to work with when you have an extra space there.
Okay, thank you.
Yeah, because then you know where your nibbles are offset. If I have 2 bytes, the first 8 bits and the second 8 bits, or actually I'm moving to the left for increasing value. So it's first 8 bits in a byte, first byte, second byte, right?
Right.
Then it's just easier visually. It's, you know, it's extra work and you don't have to do it.
Okay.
But I just find that shading in spaces helps me break it out. Otherwise, my eyes get funny and I lose my place. So, yeah. Glad you asked. Any other questions?
Also, doing that, you could look at the nibbles and you could see the hex values when you
Yes.
break it up.
Yes, you can. That's an excellent observation also. It makes parsing out the hex values so much easier because you're like, oh, I memorized my hex table. See, and everybody thinks I'm kind of nuts for spending so much time on the math up front. But when we get into the ands, or, and nots, the Boolean functions, you're going to want to know this pretty solid, and then it clicks. If you don't know this solid, it's like, oh, he's on long division and I don't even know my multiplication tables, right? He's talking about algebra and I don't know my multiplication tables. It's that kind of thing. So that's why we're doing what we're doing. And yeah, I'm glad you picked that out. That's an F, that's a Charlie, that's a 3. I mean, visually, when you start getting into cybersecurity courses, hackers look at those binary values. They're reading your email. They're literally reading your email. It comes over the wire like this or like this, and they're reading your email. And we're like, how are they so smart? They keep hacking stuff. Yeah, again, bit shifts aside, knowing this information means you can read data on a level that few people can. And that's where you impress people with the interview when you go to put in for Intel. And I will gladly write the most fabulous letter of recommendation for your interview with Intel if you work through your program with us at Computer Science at UVI as a certified Microsoft Systems engineer and a member of the Executive Advisory Board for SANS, the same organization that advises Congress and the White House on matters of cybersecurity. I will gladly write a stunning letter of recommendation for you But when you get your foot in the door and you have that interview with Intel and you want to make the big bucks in 5 years, remember this stuff. Because when you're working with chips and digital components, some of this stuff, people just know it when they get to that interview. You want to be one of those people, right? Okay. We ready for the next one?
Yep.
Yes.
Okay. Good. All right. So I didn't break this out as far on number 4. So when given a binary value of 0011, what is the hex value when it is quadrupled? So if I'm quadrupling it, I'm increasing it fourfold. That's 2 squared. That's 2 shifts to the left. I'm taking 1, 1, and I'm moving it to here. I want to keep my trailing zeros, so 1, 1 becomes 1, 1, 0, 0, or C. Wow, that was easy. Any questions on number 4?
No.
No.
Now, if I take the decimal value of 0011, what's the decimal value of 0011?
3.
3.
12.
The decimal value of 00.
Oh,
I know.
oh yeah, it is 3. It is 3.
But if you were just getting ahead. That's all.
Yeah.
Yeah. When you saw 1100, that is 12. So
Yeah.
what is 12 relative to 3? Oh, it's 4 times as much. It's 3 quadrupled, right? See, you jumped ahead and got the answer, and it was the first thing that came out of your mouth, and that's what computers do. They work on this bit level. That just, if you could see me right now, I'm smiling. Well, all right, you can't see me. I'm smiling, right? I don't know if I'm having a bad hair day. Let's see. Yeah, you snapped that right out. You knew what it was. You knew it was 12. Boom. Yeah, that's what we want. By the time we finish with this module, you'll be in good shape. All right. I'm going to mute my microphone now. Not my microphone, my video. All right, moving right along. Let's take the last one. Quadruple the hex value of 777. Don't let a trick question on the assessment throw you. Remember that this is hex and not decimal. We're not talking about an aircraft in decimal number. It's not 777. It's hex value 777. So we need to provide the new hex value. We have to use the binary values of 7, which collectively are 0111, 0111, 0111. Would anyone care to tell me how many places we are sliding in which direction? Oh, it's actually on the screen, I'm sorry. 2 places to the left, right? Because we're quadrupling, we're doing the same thing. So we're taking this and we're sliding it 1, 2 places, 1 more place here. That means I need to put a 0, 0 in front of the 1. And there's already a 0 in front of the 1, so that makes 3 0 zeros. Does everybody see what happened here? I already have a 0, but I'm sliding to the left 2 times, which bumps that 1 here. So I'm actually adding 2 zeros on the left. I've preserved my leading zeros. But I still have that pattern. 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. That's my original pattern. I'm adding the trailing 2 zeros so I don't lose my place. Now I can break that out. 1100 is Charlie. 1101 is just more, it's just 1 higher. What's 1 higher than C? D. What's 1 higher than C? D. And what's 0001 in hex? It's 1. So the decimal number is busy, but I have 1 times 16 cubed. It's 4096. I have, let's see, what's one more than Charlie? 13 times 256. That's busy. So actually, I took the Charlie value first. 12 times 1 is 12. Then I take the D here. That's 13 times 16 is 208. Take the D here, that's 256 times 13, that's 3,328. I take the last one, which is just 1, times 4096. If I add all these together, I get my result. If I take out my calculator, I get 7,644. The question is, if I cut that to a quarter, is that going to equal the decimal value? 1/4 is it going to equal the hexadecimal value of 777? So let's try that in our calculator. I'm going to insert 7,644. And, I mean, there's a number of ways you can check it, but I'm going to go ahead and clear my entries. I'm going to enter a decimal value of 7,644. Oh, you see that gives me my hex value of 1 delta delta Charlie, so I know that's right. Gives me my binary value of 0001, 1101, 1101, 1100. So I have the 1 delta delta Charlie, right? I'm going to divide by 4. And now I have a hex value of 777. Any questions on item 5?
I would like you to go over it again, please, because I still don't understand.
Okay. Let's start with the hex value of 777. I'm going to quadruple the hex value. That means I'm going to, which am I going to do, Aaron? Increase it or decrease it? If I quadruple it,
Increase.
I'm increasing it by a factor of 4, right?
Yeah.
So am I going to shift to the left or the right?
To left.
Yes, left. I'm going to take the hex value for 777 and I'm going to turn it into binary numbers. So from the binary decimal hexadecimal table, I take 777 and I do this. That's the binary equivalent of 777. Are you with me so far?
Yeah.
Okay. So I'm going to do this manually now. I'll put it down here, okay? And if I'm going to shift this 2 places to the left, I'm going to add 2 zeros on the right. Okay? Are you with me?
Yes, I'm with you.
So I'm going to do it a little differently this time. And I'm glad you asked me to do this because this is another way to do it. I'm going to add a 0, 0 here. But now my spacing is off, right? Because my nibble has become 1, 1, 0, 0 on the end. You see what happened when I shifted 2 to the left? I have to add 2 trailing zeros, yeah? Now I have a space here, but I don't really need a space here, so I'm going to take that out. And I'm going to add a space here. Okay? You with me?
Yes.
Going to do the same thing here. Take the space out, add a space here, because now my nibble boundary has changed. And I have this 0, 1 over on the left, but that doesn't look right for a nibble, does it? I have to put in 2 more zeros just so it looks right. Now if I go back to my table, my binary hexadecimal decimal table, 0001 is equal to what in hex? 1.
1.
1101 is equal to what in hex?
D.
D. 1101 is equal to what in hex?
D.
Same. Yeah. 1100 is equal to C. All right. Now let's get to this part right here, and we're going to do it a little differently. So I'm going to go ahead and extend this out here so we can see it in a slightly different way. So in the 16 to the 0 column, 16 to the 0 power is equal to 1. 16 to the first power is equal to 16. 16 to the 16 squared is equal to 256, and 16 cubed is equal to 4096. Now, if I had a hexadecimal value, okay, hold up. All right, so let's say I had a hexadecimal value of 2, 2, 2, 2. I would have to multiply 1 times 2. That would give me 2, okay? Are you with me?
Yeah, sure.
Okay, so that would give me a 2, but I'm going to go ahead and let's do the next column. I have a 2 here, but this column is worth 16. See, if this was decimal, I'd have a ones place, a tens place, a hundreds place, and a thousands place. See, this would be 1,000, this would be 100, this would be 10, this would be 1. But we're not dealing with decimal, we're dealing with hexadecimal, 16. So I'm taking 2 and I'm multiplying it by 16. What's 2 times 16?
32.
32.
32 is right. So I'm going to add a 32 right here. Down here, right? So that's my second column down here, right? Let's keep going, right? I'm taking the hexadecimal value of 2. I'm not multiplying it by 100 because it's not decimal. It's hexadecimal. I'm multiplying
Hello?
2 by 256.
Can you hear me?
You remember I told you to remember the doubles?
Oh,
If you remember the doubles,
hello? Can you hear
6
me?
times 2 is equal to what?
Hello?
Yeah, hello?
So yeah, so like, where you got the 16 from?
Okay, where do we get the 16 from?
Yeah.
That's a good question. So in the hexadecimal, hex for short, right?
Yeah.
In the hexadecimal value system, base 16, right? Let's go back. Let's go back. Shoot, hold on. Hold on. I'll get it. Oh no, I don't know. Oh, I'm gonna go to the Blackboard site. Yeah, it's in the Blackboard site. So let's look at the references, right? One of the things I wanted you to memorize was binary, hexadecimal, and decimal numbers, right? And inside here, when we're dealing with computer architecture, we have to think in different number bases. So we're used to dealing with decimals, right? So decimals run from 0 to 9. The numbers you use for 0, decimal numbers run in a single, if you only have a single digit to work with, you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then when you get to 10, now you have 2 decimal places, right? So you have a ones place, a tens place, a thousands place. That's what we're used to. In the binary world, we only have zeros and ones to work with. We can't get to 2s, 3s, 4s, and 5s. And computers only operate in zeros and ones, on or off, yes or no, true or false. The binary world is very restrictive, but the first value is a 0 and the second value is a 1. Most computers now work with hexadecimal, which is 16 characters, except that in the world of math, when you're dealing, so this is base 10, the decimal number system has 10 numbers to work with, 0 through 9, and it's called base 10 numbers. Binary has 2 numbers to work with, 0 and 1. It's called a base 2 number system. Hexadecimal, or hex for short, hexadecimal, is literally the Latin that means 16. You have 16 characters to work with, 0 through F. We learned Aramaic numbers. We learned our 0, 1, 2. These symbols we inherited from the Arabs. I don't know if you've ever had like a mathematics history course or a number theory course, but we get into some of this stuff in those mathematics courses. And these are Aramaic or Arabian numerals, those numbers, right? And when you get to hexadecimal, 16 characters, we don't have any more to work with. We only inherited decimal 0 to 10, or 0 to 9, and then 2 digits, the whole decimal thing, from the Arabs. And in numbers, you can have different number systems. You can have 16 numbers to work with, or 16 characters to work with, but you run out of these numbers. So you have to use a different kind of symbol. You have to use something that stands for 10. What comes after 9? 10. A, or alpha, is the character in hexadecimal that represents the decimal value of 10. But it's a single character. Okay? So a lot of times when we're working with digital components, they're slapping around values with letters and numbers, and it's in hex. Like this value is hex. You're going to say, well, that's also 777. Yeah. As a decimal number, it's 7 100s plus 7 10s plus 7 1s. Our mind puts all that together. We read that intuitively as 777. 7 1s, 7 10s, and 7 100s, or quite literally, 7 times 1, 7 times 10, and 7 times 100. That's what we do with decimal numbers. But if this were a hexadecimal value, we would have 16. So the first column in every number system is that number to the 0 exponent. So in binary, it's 2 to the 0. In decimal, it's 10 to the 0. In hexadecimal, it's 16 to the 0. Any number that's to the 0 power is equal to 1. That's one of those math facts that you learn in algebra, right? Okay, are you with me so far?
Yes, with you.
Okay, so here you see that I have 7, but if I'm hexadecimal, the first place is 16 to the 0, the second place is 16 to the first power. It's 16 times instead of 10 times. This is 16 squared times instead of 10 squared, or 100. So you ask, where do the 16s come from? Because this is base 16, hexadecimal is base 16, I have to multiply by this value, whatever this character is. In the example I was just showing Aaron, If I have a hexadecimal value 2222, I have to take, if this were a decimal value, I'd have 2 times 1, 2 times 10, 2 times 100, 2 times 1,000. We know that all day long. But computers think binary, and with a little extra magic, they turn that into hexadecimal. They think with letters also. And what we want you to be able to do is translate between the binary values and the hex values. So 1100 in the table I showed you, right? In the value, it's here. I ask you to memorize this table so that when you see this, you know it's equal to C in hex, or it's equivalent to the value 12 in the decimal number system. So if I have C in the second column, if I have a C right here, I have to take 12 and multiply it by 16, instead of taking 12 and multiplying it by 10. If I have a C here, I have to multiply it not by 100, but by 256. If I have a C here, I'm not multiplying by 1,000, because that's base 10, that's decimal. In hexadecimal, I have 16 cubed, which is a value of 4096. Instead of 1,000, it's 4,096. I have to take the 2 and multiply it by 4096. Okay? Does that help answer your question about where the 16s come from? Hello?
So it's basically because you got like 16 characters to choose from, essentially.
Yeah, yes. The short answer is yes. When you're working in hexadecimal, in a computer system, they only think in zeros and ones, but we bridge the gap and teach computers in programming to use hexadecimal, to convert to hexadecimal, because we can convert from there to decimal or from there to the alphabet. It's a little more complicated than what I just described, but that's essentially what's going on. So in a lot of network addresses and a lot of like IPv6 network addresses, in MAC addresses for hardware addresses, you see these hex characters. There's an awful lot of ones and zeros, or there's an awful large decimal number. That's impractical to work with. It's very practical for computers to crunch it down and work in a compact level with letters. Because if you have a few F's, you have a very large decimal number. And you have lots of ones in binary terms. It's easier for computer programs and software and hardware to translate between binary and hexadecimal, and then from there to decimal, right? So instead of having a symbol that represents the value 10, we use the letter A. For a symbol that represents the value 11 in hexadecimal, we use B. We use C for 12, D for 13, E for 14, and F for 15. When we're figuring out the actual decimal value of a hex expression, we have to multiply by these values against the base 16. So if I go back here, Aaron, getting back to your example, right? We have 2, 2, 2, 2. I'm multiplying 2 times 256 now. So I had 2 times 1 right here. That's equal to 2, right? Aaron, are you with me?
If you
Then we had 2 times 16. What's 2 times 16? That's 32, right? Now we have 2 times 256. What's that? 512, right? And now we have 2 times 4096. If you memorized your double numbers, what comes after 4096? You should know this by now, 8192. So if I add those together, now I have what the hex value 2222 is it's equal to 8,192 plus 512 plus 32 plus 2. So, Aaron, when I'm doing 1 delta delta Charlie, I'm doing the same thing I did with the 2222, except I'm using a value other than 2. So if I have 1, and I have delta, and I have delta, and I have Charlie, Charlie is worth 12. What's 12 times 1, Aaron?
12.
Right? What's D equal to?
Uh,
13. If you look at this, D is equal to 13, right?
yeah.
Okay, so stay with me. What's 16 times 13? Well, I'm going to take a calculator and I'm going to do that, right? 16 times 13. It's 208. Now let's look at this one. I have 256. What's D equal to? We just did it.
13.
13. What's 256 times 13? Well, I don't know, but let's do it, right? 256 times 13 is 3,328. What's 1 times 4096? It's not a trick question. 1 times 4096 is 1 times 4096. If I add 4096, 3328, 208, and 12, which is what I have here, I took the C and I turned it into 12. I took the first D here, multiplied by 13 and 16, then took 13 again, multiplied by 256, and took 1, multiplied by 4096, I get 7,644. Okay? The thing to remember is that when you're dealing with hex, you don't have ones, you don't have tens, you don't have hundreds or thousands. You have 16 to the 0, which is 1. You have 16 to the first power, that's 16. 16 squared, 16 cubed. We could keep going. 16 to the 4th, 16 to the 5th, 16 to the 6th, 16 to the 7th. A small hex value equals a very large number. Why does this matter? Does everybody know what a billion is? How many millions go into a billion?
A million?
Like 10.
1,000
1,000.
1,000 millions go into a billion, right? And a billion is the same as giga. So if you have a gigabyte, you have a gigabit, you have a billion bits, right? Did you know that if you take your smartphone and you have high definition on your smartphone and you record a video, in 10 seconds you probably have an 8 gigabyte video? Yes? Very large file.
Yes.
Very large file, right?
Yeah.
Yeah, it's a lot of ones and zeros. It's like 10 billion bits. How does your computer get all that? How does your smartphone get all that out on the cell network, out past the AT&T towers or the Via towers, out onto the internet? It uses these hex values because if you keep going, 16 to the 4th, 16 to the 5th, 16 to the 6th, those numbers get very, very big very, very quickly. If you keep adding letters and numbers for hex values, it's a practical number system to use when you have billions of ones and zeros. We're not worried about billions of ones and zeros right now, but we want you to understand how hex values can be used to make quick work out of binary values. And when we get to and, or, and not in a minute, you'll understand why. So it's easier to show you in the next module what that means and how that's a value, how that works better once we get to the next module. Because we're dealing with large amounts of digital information, ones and zeros. I mean, you might think that our decimal system is very efficient. But if you flew out into space and you met an alien with 8 fingers on each hand and 8 toes on each hand, their world would be very different. With 16 fingers and 16 toes, they would probably be using a number system based on 16, base 16, instead of base 10. We grew up with decimals. We know what 0 through 9 means. And when we get to 10, we know that 10 is a 2-decimal, it's a 2-digit number, right? This second place is actually the tens place. So that 1 isn't a single number, as in the quantity 1. Because it's to the left of the 0 here, it's actually equal to 1 times 10. And then if it was a third place over, it would be 1 times 100 or 1 times 1,000. So it's not just the number value, it's the place of the number value. Like, you know, which would you rather be paid? The one that's here? Or if, all right, let's say it's payday. You get to choose. I can pay you 1. I'll put it here. You get to choose between $1 or $10. Which would you rather have in your paycheck, a $10 bill or a $1 bill? I mean, we don't even think about it. We're like, what is that, a trick question? I'm not stupid, right? You know, Kentop, you know, you're getting crazy here. No, I'm trying to make a point. The point is that this value 1 is worth a lot more because it's in the second place. It's in the tens place, and we don't even think about it. If it were a 2 instead, I couldn't get away by paying you $2. I'd have to pay you 20. I'd have to give you a Jackson, right? Because the 2 is in the tens place, and that's 2 times 10. We're used to dealing with this, and it's so easy for us, we don't even think about it. When we start working with digital stuff, binary stuff, we're dealing with ones and zeros. And we have to have a very down in the trenches view of it, but then we also have to have like a on steroids, make it easier view. So when we get into large binary numbers, we represent those with hexadecimal values, and then that doesn't seem very normal to us. It's very natural for hardware, digital hardware, computers, because they turn switches on and off. They open and close circuits. It's like a light bulb coming on and off, and that's how they think. The value of what we're doing here is to help you get that the base 16 number system is really powerful. It just takes a while to get your head around. So I'm glad that you brought up the fact that where's the 16 coming from? Because it's easy to lose sight of that. It's not normal. It's not customary. It's not our habit. And what we're doing when we start looking at digital hardware is we're really looking at ones and zeros, and then when we start writing code, we're looking at larger amounts of ones and zeros, so we do this hexadecimal thing. I want you to understand where this is coming from, and I want you to be able to work either way. If you get a value like this, I'm going to say on your assessment, what's 1101 in hex? And you should be able to go, okay, I had to memorize that. 1101 is D as in dog, right? If it's hard to remember that stuff, just remember there are patterns. What's 1010? What's the same as 10? So if you have 10 doubled, That's the binary value of 10 decimal, and that's what A equals. What's one more? Add 1 to this 1010. If this were 1010 and I said, what's one higher than 1010? You'd go, oh, well, that's $1,011. Same in binary. You can put a 1 here, so it's 1011. That's equal to 11 in decimal, which is 1 more than 10, or it's B. B is 1 more than A. C is 1 more than B. D is 1 more than C. We're just adding ones. We only have 0 and 1 to work with, so if we add a 1 here, we have to carry it over. Oh, but there's already a 1 here. We have to carry it over. Up. We have a 0, a 0, a 1, and a 1. Let's look at this again. I add a 1 here. I can't put a 2 down. 2 doesn't exist in binary. Only 1s and 0s. So I have to carry this over. Now I have a 0 here. I have a 1 and a 1. I can't have a 2. We don't have 2s in binary. I have to put a 0 down. I carry it over. I can put the 1 here. That's where the 1 comes from here. So if I have a 1, 0, 1, 1, and I add a 1 to it, it carries over. Now the 1 is here, and I have 2 zeros there. Does this help explain things about binary and all that? We're going to get into that more when we get into addition and multiplication and all that next module. Yes? No? Maybe?
Yes, it do help. It do help.
Okay. So if I add a 1 here, can I put a 2 down below here? No. I have to carry this over. So I carry it over. That's 1 higher than this. If I add a 1 here, I can't put a 2. I carry it over. I put a 0 there. I have 1, 1. Now the 1's here. 0. E is 1 higher than D. 1, 1, 1, 0 is 1 higher than 1, 1, 0, 1. I want you to notice the pattern. This is 2. This is 2 right here. This is 4. This is 8. Look at what's happening to the 1. This is 1. Double it. This is 2. The 1 moves. Double it. The 1 moves. It's here. Now it's 4. Double it. The 1 moves. Now it's 8. See what's happening to the 1? It moves here, it's 2. It moves here, it's 4. It moves here, it's 8. Everybody see that?
Oh,
Everybody see that?
yes.
I notice.
Yes.
Yeah. If that clicks,
Yeah, it's not doubling now.
yeah, it's not intuitive, but if you catch it, if you catch the pattern, it's like the light bulb comes on. What's 16? Move the 1. I have a 1 and 0, 0, 0, 0. I have an extra 0 now. What's 32? I have a 1 and 0, 0, 0, 0, 0, 0. I have 6 zeros. So a 1, 0, 0, 0, 0, 0, 0, right? That's 64, I think, right? That's the same as 2 to the 6th. Put another way, how many zeros do I have here with 2 after the 1? Want another pattern that helps?
Wow.
2 to the first is 2, isn't it? 2 to the first power is 2, yes? I have 1 0 after the 1. How many zeros do I have to have after the 1 here? I have 2.
2,
What's 2 squared? 4.
4,
Right? How many zeros do I have after the 1 here? 1, 2, 3.
3,
2 cubed is what? 8.
8,
Right? If I have 16, I have 4 zeros. What's 2 to the 4th? 16. Right? That's why the pattern is important to understand. Once we get the pattern down, then we'll start worrying about addition, subtraction, multiplication, division. That comes next module. But you got to understand where some of these numbers are coming from. What is the number 7? Well, it's 7 items, and I can count them out on a table, but this is the Aramaic character that's used to represent numeral 7. We just know it as 7 intuitively because we learned that since we were a baby, right? What's this? A computer looks at this, or software interprets this as 10 in hex or in binary 1010, right? Okay,